This is a continuation of our discussion of acids and bases. In this video, we are going to look for polyprotic acids and the factors that affect the acidity of an acid. In previous discussions, we have used binary acids like hydrochloric acid. Binary acids are monoprotic. They can only donate one proton. Some acids have more than one ionizable proton. These are called polyprotic acids. The acid strengths of the ionizable protons may be different or equal. If it has 2 protons, it's a diprotic, and if it has 3 protons, it's a triprotic. Sulfuric acid is a great example of diprotic acid, and phosphoric acid is an example of triprotic acid. Polyprotic acids ionize in different steps. Each ionizable hydrogen or proton is removed sequentially. Sulfuric acid is a stronger acid than its conjugate base bisulfate. Why is that? Sulfuric acid is stronger than bisulfate because it completely dissociates in water, while bisulfate ion is a weak acid that only partially dissociates. The high electronegativity of the oxygen atoms in sulfuric acid pulls electron density away from the hydrogen, making the proton more easily donated. In contrast, the presence of the negative charge on the bisulfate ion makes it less likely to donate another proton. Polyprotic acids ionize in steps. Successive deprotonation weakens the acid, and each hydrogen has a separate Ka value, and the Ka value decreases. The less hydrogens, the weaker the acid. Most problems we face deal with the first ionization step. Observe that sulfuric acid is a strong acid and only has 1 Ka value, but sulfurous acid is a weaker acid because it has 1 less oxygen and it has 2 Ka values. Phosphoric acid is a triprotic acid very important for our lives. The phosphate buffer acts in the cytoplasm of a cell as a proton donor and a proton acceptor. It is maximally effective at pH close to xpKa, which is 6.86, and it tends to resist pH changes in the range between 6.4 and 7.4. It is therefore effective in providing buffering in intracellular fluids. Human blood plasma has a pH of 7.4. Should the pH regulating mechanisms fail, like in uncontrolled diabetes or overproduction of metabolic acids, the pH can fall to 6.8 or below, leading to irreparable cell damage or death. So that is important to understand the equilibrium of phosphoric acid. Acids differ in their proton donating ability. Strong acids like hydrochloric acid react completely with water, whereas acetic acid reacts only slightly. The exact strength of a given acid is described by the Ka value, the acidity constant. What are the factors that can affect the acidity? The first one that I'm listing here is the bond polarity, and that has to do with the presence of an electronegative atom bonded to the hydrogen. We know that chlorine is an electronegative atom that is pulling electron density from the hydrogen, making it easy to donate the proton to a base. Now, when we have a cation, that will be stronger than a neutral molecule. And in this case, we have the example of water. We say water is pure. If it's pure, it's pH 7, it's neutral. And then when we have hydronium, that is acidic. Now, the next one is that neutral is a stronger acid than the anion. And for that example, we say here, water is a stronger acid than hydroxide, and then ammonia is stronger as an acid than NH2- after losing that proton. So we also have more examples to show, and that is related to the content of oxygen atoms. The strongest acid in this table is perchloric acid, which corresponds to the weakest conjugate base, perchlorate ion. Acidity increases on the left from bottom to top, making hydroxide ion the weakest acid. Hydroxide is the conjugate acid of oxide, oxygen 2 minus. The greater the number of oxygen atoms in oxoacids, the stronger the acid. Observe the most acidic acid on the left table is perchloric acid, and that the oxidation number for chlorine in yellow in the formula of perchloric acid is increasing from +1 in hypochlorous acid to +7 in perchloric acid. Nature is rich in carbonyl compounds and weak acids, carboxylic acid groups. We have seen the equilibrium expression for vinegar and know that most organic acids have Ka values near 10 to the -5. Because acidity constants are expressed with exponentials, when we study organic or biochemistry, we usually work with the logs of the ionization constant, what we call pKa. Now we know that pKa is minus the log of the acidity constant, and what I want to show you with this table that we have several pKa's and these structures of when we have acetic acid, vinegar, that is replacing hydrogens, and we start for acetic acid with a pKa of 475 as a weak acid, but by replacing hydrogens and bringing chlorine atoms, we have a more electronegative atom chlorine now that is pulling electron density, making it easier to donate the proton on the OH. Now we started with pKa of 475 and ended off with the pKa of 0.64. The message is that the lower the pKa, the stronger the acid.